Good morning. We were looking at transformers in the last class, and I mainly discussed about the no load condition of the transformer. To summarize what we saw in the no load condition, we said that the transformer will draw, the primary will draw very minimal current under no load condition. To make sure that the flux is established, which links with the flux is established in the core, which links with both primary and secondary winding. And in the process, you are going to have some losses that are incurred. So core losses are incurred in the transformer. And this is actually consisting of two components. One is hysteresis loss, which is proportional to frequency, and eddy current loss, which is proportional to frequency square. And because of this, we said that the current that is drawn during the no load condition, the minimal current which is drawn during the no load condition or open circuit condition of the secondary will consist of two components of no load current, I0. So this is the no load current. This is actually going to consist of, one is the core loss component of current. This is actually a fictitious current. Core loss component of current which will be drawn to satisfy the real power loss component of the transformer core. Okay, and the other component of current is going to be the magnetizing current. So magnetizing current is the one which is responsible for establishing the flux. That's what we said in the last class. And we said that generally the magnetizing current is also small because the reluctance of the core is very minimal. The permeability is pretty high for the core material. But nevertheless, if I compare these two, in that also core loss component of current generally will be a smaller fraction as compared to the magnetizing current if I compare it with the total value of I0. So if I say that the total value of I0 is something like 0.5 ampere, for example, the magnetizing current will be as high as 0.45 or something like that, and the core loss component of current is going to be smaller. In fact, from the phasor diagram we drew yesterday, we can say that IC square plus IM square root of this will give me I0, because we had drawn actually in the phasor diagram as though this is the common factor between the two windings, that is primary and secondary. So this is the flux. So I'm going to have the magnetizing current in phase with the flux, for example, and I am going to have the voltage which is actually going to be perpendicular to this magnetizing current. So this will be V1. So if I look at the core loss component of current, that will be in phase because it is a real power loss component current. So this is going to be IC. This is going to be IC. So this is IC and this is IM. And when I add both of them, what I get will be I0. So I0 is going to be displaced from V1 by a pretty large angle. So this is going to be phi no load or power factor angle under no load condition. So power factor angle under no load condition is going to be a large angle. So I should say definitely that the no load power factor, which is actually cos of phi no load, that is going to be really small. So this will be only of the order of 0.1 or 0.2. Maximum this will change from 0.1 to 0.3, nothing more than that, because we tend to reduce the eddy current losses as much as possible by laminating the core. So this eddy current losses are reduced by laminating the core. Whereas hysteresis losses, of course, depend upon what is the original property of the material we are using for making the core. So that depends upon the BH loop, what I see for the core. So that's not really going to, it is not going to be possible for us to reduce that specifically unless we kind of play around with what kind of core material we use. Whereas eddy current losses can be minimized by making the laminations as thin as possible. So that is the reason why we may have the laminations generally only of about 0.3 mm to 0.6 mm. That will be the thickness of each of the lamination that we are using in the transformer. That is the way it is going to be. Okay. Now let us try to explore what happens to the transformer when we are connecting a load on the secondary side. Okay, so let's try to take a look at this. So what we are looking at is, like, let's say this is the transformer core, and I'm again showing on one side, I'm going to have the primary winding, and on the other side, I'm having the secondary winding. Okay, and I'm connecting a voltage source, AC voltage source V1 to this primary winding, and initially when it is on no load, it is drawing a very small current by name I0, and that is going to establish a flux in this particular core. So I'm going to have the flux which is established in the core, which is somewhat like this. So this is going to be the path for the flux. Now I have got the value which is coming out here, let's say, is E2. I'm going to make a few assumptions before I start the analysis under load condition. First of all, I'm going to assume that resistance of the winding, I'm going to assume right now them to be 0. Resistance of the windings are 0. That's what I'm going to assume. And second thing, I'm going to assume that core loss in the transformer's core, I'm going to neglect it. Okay. And the third assumption that I'm going to make is, just for simplification, N1 equal to N2. The number of turns in the primary and secondary are equal to each other. Let me just assume it that way initially to analyze this particular transformer's action. And I am going to connect a resistive load here. Okay, so this is going to be the load that I have connected, simple resistance I'm connecting. So if I try to look at what is the kind of waveforms I'm going to have, let's say I'm applying a voltage which is actually V1. So I'm going to apply a voltage which is V1. So I'm showing V1 like this. This is with respect to omega t I'm drawing. So this is V1. What I have drawn here is V1. The magnetizing current of the transformer, because I am neglecting core loss component of current, I should say IM equal to I0. Right now, I am not going to include IC at all. IC is neglected. Okay. So I'm going to have Im equal to I naught. So if I draw what is the magnetizing current, I'm going to have the magnetizing current to be really a small value, but that will be lagging behind the voltage by 90 degrees. So I'm going to have the magnetizing current somewhat like this. So I'm going to draw a very small value of current and I show it like this. This is what is the magnetizing current. So this is going to be Im or I magnetizing. Okay, so obviously the flux will also be exactly having a similar waveform, but only thing is it will be of a much larger quantity hopefully, because the reluctance is very small for the core. So I should be able to show the mutual flux probably really peaking like this. It's going to have a very large value and it's going to, you know, flow through the core alone. Primarily, it will confine itself to the core. So this is going to be the mutual flux, which is linking both primary and secondary. So this is the way I'm going to have the mutual flux. Okay. Now, once I connect the load, as we spoke earlier, I'm going to have a current which is I2 that is flowing through the load. This I2 will set up a flux in the core. If it is allowed to set up a flux, it will set up a flux in the core in such a manner that it is going to be exactly opposite to that of the original flux. So this is going to set up a flux in such a manner that it is going to flow this way. This is going to be the kind of flux that is set up by the current that is drawn by the secondary winding or the load. So that is going to be I2. So I2, if I assume this is resistive load, that will be in phase with E1 or E2. So I am going to have essentially a current which is drawn by the transformer's load. That is not going to be as small as the magnetizing current. Magnetizing current is small because the reluctance of the core is small. So it is going to really draw very small current to establish even a larger flux, because MMF divided by reluctance is going to be the flux that is set up in the core. And the flux that is set up in the core, although it is of a finite value, very small MMF should be sufficient to set up this flux because the reluctance is small for the core. So I magnetizing is really, if you realistically look at what will be the typical values, let me probably again take this 2.2 kVA 220 by 110 volts 50 hertz transformer, for which we worked out some problem. So if I take typically something like this, we can say in this particular case, the rated current, if I try to look at the rated current for the primary or for the high voltage side, let me talk about 220 volts as the high voltage side and 110 volts as the low voltage side. Relatively, I'm talking about this. So on the high voltage side, the rated current will be 2200 divided by 220. Which will actually give me, this is volt ampere and this is volt. So I'm going to get the ampere and that is going to be 10 ampere. So if the rated current happens to be 10 ampere, generally the magnetizing current will be less than 5%. This is the thumb rule. Normally it will be less than 5%. It can be like 2%, 3%. So I am going to have essentially only about 0.2 or 0.3 ampere being drawn as the magnetizing current, nothing more than that. Very small value of current is drawn by the transformer primary winding to establish the flux. So that's what I'm trying to get at. This is really small. Whereas if now in this transformer itself, the rated current is 110 to 2200 by 110 on the secondary side. So that is going to be 20 amperes. Right? So this 20 ampere of current, if I have to draw, obviously I'm going to have a resistance here connected in such a way that 110 divided by 20 is going to be the resistance what I have here. So it is approximately 5.5 ohms or something like that. So this is going to be the resistance that I am connecting such that the current is flowing, which is actually equal to the rated current value. Okay. So this 20 ampere is now flowing through this particular core, particular winding, secondary winding. And when I am actually looking at the secondary winding drawing so much of current, obviously the primary is going to make sure that it takes sufficient amount of current to nullify the effect of the load current so that the original flux is not killed. So definitely this is going to again draw a current in such a way that N1 I1 equal to N2 I2. So if I assume N1 equal to N2, I'm going to have I1 equal to I2. So originally, although only 5% of current was flowing through the transformer, now 100% current will flow through the transformer windings to ensure that the load current is supplied appropriately from the primary side and yet the flux is not killed. So I am going to see that the current what I see in terms of either I2 or let me call this as I1 dash, which is reflected on the primary side. So that is going to be somewhat like this. So let me draw that current. So that current is going to be almost in phase with V1 as well as E1, E2 and so on. So I'm going to have a very, very large current. The fraction that I have drawn is not correct. Please note, this is magnetizing current. This magnetizing current is not 5% of what I have drawn. So I'm not drawing to scale. But all I'm trying to get at is this current, which is the load current, which is I1 dash or I2. This is going to be basically pretty large as compared to what I am looking at as the magnitude of the magnetizing current. Okay. So I have I1 and I1 dash as well as I2. Both of them actually are pretty largish as compared to IM. Now these are establishing a flux we said in the core. But because the mutual flux is already established in the core and it is not really allowing any other flux to be opposing itself because the primary is coming to the aid of the mutual flux to make sure that it survives. So I'm going to have I1, I2 establishing a flux, but that is not going to find an easy path through this. So it will try to somehow survive by circulating only through the air gap like this. So I'm going to have the flux that is set up because of I2. It is going to go around like this through the air path, which is actually leakage. We call this as leakage because it is linking only with its own self. It's not linking with the primary winding at all. The same way, whatever the primary was trying to set up in opposition to the secondary side load currents flux, that is also going to set up its own flux, but that is also not going to find much path here because the secondary flux will oppose it. So you are going to see the primary sets up its own leakage somewhat like this. You are going to have the leakage flux somewhat like this for the primary. So we are going to see that there is some amount of leakage set up in the transformer's magnetic circuit only after the load current starts flowing. And after the load current starts flowing, both primary and secondary will have their own leakage fluxes set up. So if I try to draw the leakage flux, let me draw that also in green, but Just to say, because it is flowing through the air gap, the reluctance is very, very large. The current is large, but the reluctance is also extremely large. It's almost 1000 times. The current may be only about 20-25 times, because I told you that magnetizing current is 5% or less than 5%, whereas you are going to have the rated current almost 100%. So compared to 5% or 4%, the 100% component is 25 times. Whereas if I compare the reluctance, the air gap reluctance is going to be more than 1000 times that of the reluctance offered by the core. So I'm going to have a very, very small amount of flux that is set up, which is going to be somewhat like this. So this is going to be the leakage flux that is set up because of either primary current or secondary current. So this is going to be the leakage flux. So the leakage flux will increase as the load current increases. If I am connecting a 5.5 ohm resistance, I get 20 ampere current. If I am connecting 10 ohm or 15 ohm resistance, I'm going to get lower and lower ampere of current that is passing through this particular secondary winding, which means the primary reflected current will also be smaller, because ampere turn balance has to be maintained no matter what. So I am going to have always the leakage flux dependent upon how much is the current that is flowing through the secondary winding or load. So the load current dictates how much is the leakage flux, whereas the magnetizing current dictates how much is the mutual flux. And the magnetizing current is not going to change much, because for a particular voltage and particular frequency, a particular flux has to be established in the core. So the magnetizing current is going to be a constant value. Okay, so there are going to be mainly two components of flux in the transformer under load condition. When a transformer is on load, you are going to have two components of flux. The first component of flux is essentially due to the magnetizing current. That is going to be the mutual flux. And this is going to be a constant because it is established based on the applied voltage and frequency. So this is going to be a constant irrespective of the load on the transformer. This is essentially going to be depending upon what is the voltage and what is the frequency. V by F, that is going to decide how much is the flux. The second component that exists during the load condition is leakage flux. This is essentially set up not in the core, it is mainly through the air gap. So the leakage flux links with its own member which carries the current. So if the primary is carrying a current, it is setting up a flux around the primary itself. It will not link with the secondary. The same way, if the secondary is carrying a current, the secondary will establish a flux through the air gap, which links only with the secondary winding. So this is essentially going to link with its own self. And this will depend upon, this will be proportional to the current carried by the winding. Because the air gap reluctance is not going to saturate, or it's not going to change. So as the current increases, correspondingly there will be a small increase in the flux. It's never going to hit saturation, right? That is the reason why you can say the leakage flux will be proportional to, this will be proportional to whatever is the current, because that is the MMF which is causing the leakage flux. So that is going to increase along with the increase in the current. So if I try to draw the phasor diagram corresponding to this, I should say this is V1 and I'm going to have a flux which is common to both primary and secondary. So let me show E1 and E2 on this side. So I'm going to have V1 equal to E1, which is also equal to E2 if I assume number of turns in the primary and secondary are one and the same. Now if I connect a resistance as the load, then the current what I see will be in phase with E2. So I'm going to have I2 somewhat like this, which is flowing through the transformer secondary winding. The reflected current I can draw on the other side, and if I assume the turns ratio is 1, I should show a current which is almost having the same length as that of I2. So I should show this as I1 dash. This is the reflected current, reflected component of I2 on the primary side. So this is the reflected component of current which is increasing because this I2 is trying to kill the original flux. On the other hand, if I show the magnetizing current, I should show the magnetizing current somewhat like this. This should be IM. This is the magnetizing current which is actually 90 degrees away from the voltage and it is lagging behind by 90 degrees, right? Now this I1 dash and IM, if I add, that is going to be the total current that is carried by the primary winding. Please remember this IM is less than 5% of I1 dash. So really the phase angle what I am seeing here, it may not be anything much because this current itself is pretty large, whereas this current is very, very small as compared to I1 dash. So this is the total primary current. So this is the kind of phasor diagram we are going to have for the transformer when it is on load condition. That too when we don't consider the resistances of the transformer, when we don't consider the core loss component of current of the transformer, and when we don't consider that N1 and N2 are different from each other. They are one and the same. That's what we have assumed currently. Okay. Any questions on this? Any questions? Is this clear? Please read from either Smith and Dorf or Edward Hughes. It will be very helpful if you read, because whatever we tell in the class, to make sure that you absorb that properly, I think you should study from a book. So please do study so that it gets reinforced. Okay. Now that we have seen that this leakage flux is going to link with its own member, that is, if it is the primary that is producing the leakage flux, it is linked with its own primary winding alone. And similarly, secondary flux, secondary leakage flux, what is produced, it's linking with secondary leakage alone. It can be manifested as a drop. Anytime a flux links with this particular member, that is the winding, then it is going to definitely have an induced EMF due to leakage. So if I call this as leakage, this leakage flux is definitely going to cause some amount of induced EMF within its own member. So that particular induced EMF, which is going to oppose, for example, if I have an induced EMF corresponding to the leakage flux of the primary winding, it is going to oppose definitely V1. which is trying to push a current in this direction. So we attribute that to something like an inductive drop, because the flux is always manifested in the form of some kind of reactive power or inductance. So we are going to say that this leakage inductance, leakage flux, which is going to induce an EMF in the primary winding, that can be considered as a drop, which is an inductive drop. So that is the reason why generally when we draw the transformer, we say that basically this is probably the primary winding and this is the secondary winding, and what it has as the induced EMF is E1, and what this has as the induced EMF is E2, and we are going to have E1 by E2 equal to N1 by N2. And this E1 and E2, what is induced in the transformer, we consider that it is due to the mutual flux. But what is going in the form of leakage, we are going to show it as an external reactance which is connected away from the mutually coupled primary and secondary winding. They are not separate in actual reality, but we are showing it so that for calculation purposes, we will segregate the mutual flux. The mutual flux also is passing through a core. So this is actually the indication for the core. If it is iron core transformer, then you will show these two lines. If it is an air core transformer, you will not show these lines at all. If you just put two coils which are coupled to each other just by air, the medium that is existing between them is air, then you are not going to see these two lines, or you are not going to indicate these two lines. So this is the ferromagnetic core which we are indicating here. So this is the ferromagnetic core. Now we are going to see that this we call as the leakage reactance drop corresponding to primary winding, and this is the leakage reactance drop which is due to secondary windings leakage flux. So we call this as, say, X1, and we call this as X2. Okay, and we have assumed right now there is no resistance. Of course there will be resistance, but right now because we assumed it is not having any resistance, we are going to have V1 here. From E2, whatever voltage is dropped in the leakage reactance of the transformer, after that we show this as V2, which is the terminal voltage of the secondary winding, and here I am going to connect the load. The load is connected here. So what is flowing here? I may call this as I2. And what is flowing to establish this flux? I call that as IM. And what is actually reflected from here? So if I write here, that should be I2 dash. But I2 dash plus IM put together, what I will see here is I1. So I1 will be equal to IM, which is 90 degrees lagging from the voltage, and I'm going to have I1 dash, which is the reflected component from the secondary side into the primary side. So this essentially tells us that the leakage of the flux is a wastage, because whatever is the voltage you're applying, some drop takes place, and after the drop, whatever is left over, only that goes to establish the mutual flux. So it is such a waste of the energy that you are supplying or the voltage that you are supplying. So it is always essential to reduce the leakage as much as possible to improve the performance of the transformer. So what do we mean by improving the performance of the transformer? The performance of the transformer is measured from two viewpoints. One is the efficiency of the transformer itself. So what is the input power and output power? So the performance is measured in terms of efficiency, which is actually how much of power transfer takes place from the input side to the output side. So this will be output power divided by input power. That is the efficiency. And the second thing normally we look at in a transformer is very often it is meant for stepping up the voltage or stepping down the voltage. So if I apply 220 volts here, I expect 110 volts here exactly. If instead of 220 volts, if I apply the same 220 volts, but some voltage is dropped here and some more voltage is dropped in this. In that case, I'm going to get instead of 110, I'll get 108 volts. Maybe I'll get 108.5 volts. So I'm having a voltage drop because of the leakage reactance. So I definitely need to say how regulated or how dropless the voltage at the output is. So this is measured by voltage regulation. So voltage regulation is whatever is the expected voltage ideally minus real output voltage. What is the actual output voltage? Okay, rather than saying real, let me say actual output voltage. So the voltage regulation is an index of how much is the drop that is taking place within the transformer itself. So I want to make sure that I'm not going to have a huge amount of voltage dropped in the transformer. I am not going to have huge amount of copper losses or core losses take place in the transformer so that the efficiency is better. So if I want to really minimize the voltage drop, I should minimize the leakage. So the leakage has to be minimized. So voltage regulation can be improved. This can be improved by reducing leakage. So how do I really reduce leakage? So leakage flux is that component of flux which does not link with both the windings. So how do I reduce leakage? So ways of reducing leakage. How do I reduce leakage? So one major thing that can be done to reduce leakage is if I call this as the transformer core, this is the transformer core. If this is the in-between portion between the primary and secondary, I call this portion as window. So as I told you, the leakage is generally going to flow through the air gap. So if I make this window longer and thinner, so making the window longer and thinner, that will actually increase the reluctance of the air gap path. Because the longer the air gap path is, the reluctance offered is going to increase, because you know that the reluctance is equal to L divided by mu naught A. So if the L increases, then the reluctance of the air gap path increases. So which means less and less number of lines would like to go through that path. They will try to refrain from following that path, or the amount of flux established because of the leakage will be reduced further and further. So when you make the window longer and thinner, first of all, you're going to have the air gap leakage flux is going to decrease. So that is going to essentially reduce the leakage reactance. So that is one normal, kind of strategy that is followed in many of the transformers to make the window much thinner and longer. So that will improve actually the performance of the transformer in terms of having reduced voltage drop. The voltage drop will not be as much. The second thing is this kind of construction where I'm going to have one winding wound on this side and the other winding wound on the other side, and the core is somewhat like this. You can see that this side is not surrounded by iron. So there is no iron or ferromagnetic material on this side of the winding. So also there is no iron on this side. Whereas on this side of the winding, you have the iron core from the other limb. So if I want the reluctance to be maintained uniformly large for mutual flux, then I can actually think of something called shell type construction. Core type construction is going to have less amount of iron being consumed because you have two limbs, and on either limb you are going to have one winding wound. Whereas in shell type construction, what we do is somewhat like this. I am going to have a core somewhat like this, and I am looking at this as one of the window, this as another window, and I'm going to have the primary wound here. Maybe secondary also is wound around this. So if you look at the primary and secondary, on either side you are having iron core. So this is also iron core, this is also iron core. So the winding is completely surrounded by iron. So whatever flux it is producing, it might take two paths like this and like this, but you are going to see that it is going to confine completely to iron. It will not go through the air at all, and both windings are linking with all the flux. So shell type construction is commonly used wherever the leakage cannot be tolerated, but shell type construction definitely requires more amount of iron to construct the same kind of kVA rating transformer. Still you will require a huge amount of iron in that case. Third strategy that is very commonly used again to reduce the leakage is sandwiched windings. You are not going to have primary and secondary winding completely segregated from each other. Rather than that, let us say I'm going to have the core somewhat like this. So I have the core here. Rather than segregating the primary and secondary on either of the limbs, I might have actually some portion of the primary wound here. Then I'm going to have the secondary. Then I may have again the primary, and I may have some secondary. So I may have again primary and secondary wound on either side, right? Sandwiched between each other. So it is going to be called, that's why it is called sandwiched winding. Of course, you have to connect these two. This green and this green has to be connected, and maybe this green and this green has to be connected. And this is one terminal that has to be brought out, and this is another terminal that has been brought out. So this is the kind of construction I'm going to have if I2 is flowing through this, and I2 will get out of this. The same way, the black windings which I have shown as primary, so those also, so this is, let us say, primary, this is secondary, this is again primary, this is secondary, this is secondary, whereas this is primary. So I'm going to have one after another. The primary and secondary windings are sandwiched among themselves. So you will not have completely one side the primary flux or leakage flux, which is not linking with the secondary at all. That will not happen. So when you sandwich the windings together, then the leakage is minimized automatically. And the fourth one, which is again very commonly used, is concentric windings. So in this particular case, if let us say this is the core. So I am going to have, let us say, my primary winding wound like this. And maybe I will have some portion of the primary here too. So these two will be connected together and I'm going to have this entire thing as primary. So this is I1 and this is I2, I1 coming out. Now the secondary, if it is a high voltage winding particularly, I will put it around this. So I'm going to have this winding surrounding this, and the same way in this case also it can surround this like this. So if I look at the cross section, if this is the core, I am going to have the primary winding somewhat like this. So this is going to be the primary winding. And around that, I will have the secondary winding. So my secondary winding is going to be somewhat like this. This is going to be the secondary winding. So this is secondary or high voltage winding. If I say this is a high voltage winding, because please remember, I am going to have the core also as a conducting material. So the low voltage winding as well as high voltage windings, they have to be insulated from the core. I cannot simply wind it without insulating. I have to have the copper insulated with plastic or something like that, and then only wind it around the transformer. So if it is a low voltage winding, thinner insulation is sufficient. Whereas high voltage winding, thicker insulation will be needed. When it is thicker insulation, it will be easier to make a bigger circle and it is easier to put it outside. And if it is a thinner insulation, it is easier to put it inside. So that is the reason why secondary winding or high voltage, I need not say it will be secondary always. It depends upon whether it is step down or step up action. If it is a step up action, the secondary winding is going to be of higher voltage rating. And if it is a step down action, I'm going to have the primary winding is of higher voltage rating. So this is going to be the primary winding. And the primary winding in this particular case, if I assume it is the low voltage winding, so that is going to be put in the inner circle. So this will be primary winding, which is actually a low voltage winding, which will be put inside, and secondary winding will be arranged around this. So it looks like concentric circles. That is the reason why we call this as concentric windings. One winding will be surrounded by the other. Very often in most of the transformers, what you would see is the core will be available in the form of stampings of this particular laminations of this shape. So what you will see is there will be many laminations like this, and all of them will be stuck together. They will be stuck together with the help of some kind of resin after insulating them from each other. That is to reduce the eddy current losses. Now you would put one winding around this like a ring. So you can insert the winding somewhat like a ring. So this is inserted here. The same way I'm going to probably insert the primary winding like a ring. Now the secondary winding will surround it, or if it is like a sandwiched winding, I'm going to have the secondary winding also put forth like this. So it is going to be like another ring, which is put forth around this particular limb. Now from the top you would just put another stamping and close it after these windings are inserted. So you will have again the stampings that are again arranged one behind the other. So this is a portion of the core which is finally, assembled. And this is one portion of the core which is in either U-shaped or L-shaped. So you will have many cores somewhat like this. You may have the core L-shaped and you may have another L shape like this, and you may try to, kind of close them down with each other. So you can have one L shape from here and another L shape from here, or you can have U shape. Sometimes you will have E shaped cores, something like this. So you may have one core having three limbs like this. Okay, so you can have an E-shaped core which will be top, closed from the top again. So you can have these kinds of constructions possible in the transformer. So in these cases, I will be able to insert the windings here. I can have, the primary winding probably put up like this. This is the primary winding, and I will have one more primary winding here, and I can have the secondary probably put on the top of this. So I can have one secondary here, second secondary here, and third secondary here. So I can have basically these kinds of constructions to reduce the leakage so that the performance of the transformer improves. Okay. Until now, I neglected the resistance of the winding. But obviously, even a copper winding is going to have a resistance. So if I try to draw the complete equivalent circuit of the transformer, I should show it as though, let us say, I have again the representative diagram of a transformer which is having primary winding here and secondary winding here. And I'm going to show this in the form of equivalent circuit. So I will have to have a primary resistance, primary winding resistance R1, primary winding leakage reactance which is X1, and I'm going to have, after the drop in all of them, I'm going to have the voltage E1 induced here. Okay, that E1 induced EMF is due to the mutual flux between the primary and secondary. What I am applying here is V1. Now I'm going to have an iron core which is making sure that the primary winding and secondary winding are mutually coupled with each other. Primary winding is having N1 turns and secondary winding is having N2 turns. So because of the mutually coupled flux, I'm going to have E2 as the voltage that is induced in the secondary winding as well. And I should have E2 by E1 equal to N2 by N1. And E2 is what is contributed by the mutual flux, and the mutual flux is established after whatever has been eaten away by the resistance of the winding in the form of a voltage drop and the leakage drop, whatever I have got. So now after this, I will have definitely resistance of the secondary winding, and I will have the leakage reactance of the secondary winding, and I'm going to connect the load here. So this is the load current which is taken by the transformer secondary side, and that is being supplied by the secondary side of the transformer, and you are going to have now that reflected on the primary side, and I may call that as I1. which is actually I1 dash plus IM. Okay, so we will expand upon this further in the next class regarding the equivalent circuit of the transformer, and as we go along, we will take all the non-ideality